Hey ladies and gentlemen, so I've made the repo for this project and every video will have its own branch and the next video will branch off the previous one. So when you go to the repo, don't expect the main branch to have any progress, but instead look at the branches that are available. So here's my GitHub. As you can see, main is just based off video 2. That's when I started the repo. And then if you want to go to the code that's related to video 3, video 4, and so on until I'm done with the series. In this video, we'll start defining our frame structure and any frame IDs that occur to me right now. And you guys have to understand that this is a work in progress. So I'm going to open up this project that you see here. I'm just going to open it up in VS Code because it's much easier or more pleasant to look at rather. Okay, so here's the project. It's opened in here in Visual Studio Code, and I'm going to go to the include folder and I'm going to make a new file. It's going to be called frames.h. And we'll have our normal frame guards here. Header guards. And I'm going to go ahead and paste the little frame format drawing that I have. Okay, now you guys also have to understand that the current frame structure that you see right here is subject to change as I continue to develop the bootloader. And if or when the shortcomings of the current structure arise, we can handle them accordingly. Basically, nothing right now is set in stone, but I will not change anything off screen. In other words, I will always explain in a video any changes that I have made to the file or to the overall structure of the bootloader. So this is the main structure of what I'm going to call a frame. You have this sort of start of file section here, which is going to be 4 bytes. You will have a frame ID that will tell the microcontroller and the host computer or other microcontroller, whomever is sending the firmware, is going to tell it what type of frame this is, the length of this data field. So this data is going to contain 16 bytes or 5 bytes. This will tell the host or the application receiving this frame the length of this data. A CRC field for validating our data, and the end of frame delimiter. Now, this sort of structure is going to be the basis of communication. In other words, any communication between microcontroller and the host device or computer or whoever sending the firmware will always be in terms of frames, and frames will always be of the same exact size, even if it's a simple ACK or NAC. This adds the simplicity of always having a known frame length and removes some of the complexities from having to parse frames of different lengths. When the frame being sent has no meaningful data, like an ACK or a NAC frame, then you can just ignore the payload or this data field, which I sometimes call payload. If the frame that I'm sending, if the meaningful data in it is only 2 bytes long, then the length will say, that only 2 bytes mean something. However, the rest of the bytes have to be filled. What do I mean by that? For example, for my STM32F4, I can only write, I believe it's 16 bytes. So N is always going to be 16. So what you're going to see now as I develop this bootloader is my data or payload is always going to have 16 bytes. Even if I'm sending an ACK frame, which we'll see in a minute, that's going to just be a frame ID that I've defined to be an ACK frame, and then the length will say that, I can make it say 0, I can make it say, it doesn't matter what the length says, because the data in the ACK frame is going to be meaningless. I'm only concerned about the frame ID. When I'm sending firmware, then it becomes meaningful. For example, if I'm sending 1 kilobyte of data, it's going to have to be sent in chunks of 16 bytes at a time. So every frame that I send is going to tell it that, hey, 16 bytes of this right here are useful. At the very end, let's say the last frame, let's say there's only 3 more bytes that I need to send, and I'll complete sending the firmware. So that last frame, the length will say 3, and I'll have 3 bytes here that actually mean something, and then the rest of the bytes, I still need to put something. It can be zeros, it can be all FF, it doesn't matter. The point is that length is what's going to tell the firmware how much of these 16 bytes actually mean something, whether all of them or just some of them. And I hope this is making sense. Yeah, so let's start defining some things. I'll start first by defining some start of frame and end of frames. Again, this is just Eddie in hex, and the word fair, Eddie Fairchild, in hex. So this is going to be the start of frame, and this is going to be end of frame. Now these numbers mean nothing. There's nothing special about them. What matters is consistency. So this value here, these 4 bytes, is what's going to go here, start of frame. So every single frame, no matter what it is, will always have this number right here in the beginning. And again, this is the end of frame. So this number will always live here at the end. So that is always going to signify my start of frame and my end of frame. Now I'm going to go ahead and add some more little defines here. Okay. So these are types of frames. Let's call these, let's just call these frame IDs. Because these numbers, well, no, not that one. Actually, these right here, these 2 are the start and the end. I'll call these just delimiters. Okay, so these just signify the beginning and the end of my frame. These are the actual frame IDs. So I'll have a frame called the header. This frame is going to send information. Let me just comment that. Say sends info about firmware. Let's say, for example, the size of the firmware, version, things of that, right? Again, this is a work in progress, so we still have a lot of things to think about and come up with. So this frame, all these defines here are frame IDs. So all these values will go in here, right? So if I'm sending the header, I'll type in this in my frame and so on. So the header is going to be that. It's just going to send info about the firmware. The status check will be something that if the, let's say the computer or whatever the host is, wants to just make sure that everything is okay, it can send this frame, the status check frame, and then the microcontroller will reply with like an act frame, for example, saying that, hey, everything's okay, or I'm alive, I'm here, and I'm listening. This frame right here, the start update frame, will be sent right before we start the update, so that the firmware knows that it should expect the next frame to be a firmware frame. The Uart function that we're going to make at the moment is going to live in bootloader.c. And bootloader.c and bootloader.h right now are sort of my main kind of file, my where everything is going on. Eventually, bootloader.c and bootloader.h are going to be just a library that you include into your project, and you will be able to use the bootloader and configure it. Even though right now it is bootloader.c is my actual application. Eventually, it's going to be a library that will be hardware agnostic. But at the moment, everything's going to live on bootloader.c, and this is where we're going to make this Uart send function. Another thing to note is that ultimately also this Uart send function is going to be passed into the bootloader. via a different structure that we can make to configure the bootloader. So this is going to be a structure just, for the frames. We can have another structure that's going to be called struct to configure the bootloader. This structure is where you're going to pass functions that the bootloader can use, for example, to send something through Uart, which obviously the bootloader needs to do. However, I don't want my bootloader to be hard-coded with a HAL Uart STM32 function. I want it to be able to send it on a TI microcontroller, on a Maxim microcontroller, NXP microcontroller. It doesn't matter. So you, the user, will need to provide a Uart send function, which you're gonna point to the bootloader or something like that, and then the bootloader can use that function. So that's exactly how we're gonna make this entire bootloader be hardware agnostic, where it will have the functions that it needs, but it doesn't really know or care how they work. You will have to do that part. I'm going to make a separate video on that topic alone. So let's go ahead and let me go ahead and copy my Uart send function, if I can find it in my other file. Here it is. Okay. So at the moment, obviously this is going to be hard coded. Gonna go ahead and make that look pretty. Okay, so here's my Uart send function. Let's make this bigger. And it's just a simple function that we're going to give it a pointer to 8-bit data, obviously, because the Uart could only send 8-bit data. And we're going to give it a length. So this is something that should be very trivial for us at this point. Obviously, just going through a for loop through length, and then we're setting the data into the data register of the Uart. We're waiting until the transmission is complete. Etc, etc. Then once we're done with the loop, we're waiting for the TX to be empty. Then we're waiting for transmission complete at the end. So this is a very simple function, guys. Nothing magical going on here. Gonna go ahead and make a prototype for that. Where are my prototypes? Here we go. I forgot to mention, I did make some changes to the file. And it's just these just simple dividers, because sometimes it could get very messy to look at. And all these squigglies are, what is this, unsigned? Okay, because I don't have unsigned int 32, standard int included anywhere, even though it's included in the Cube IDE, but VS Code doesn't know that, so we can just include it. It won't hurt. And that should make those squigglies go away. Okay. So now we have that simple Uart send function. The next order of operations is to make a function that will use this, and that function is going to actually send an entire frame through Uart. So of course I'm going to go ahead and paste that right under this Uart function, send function. Now this frame send frame function, what it does is it takes a frame format type, which is what we've defined here in our frames.h, and it's going to take that as a parameter, and I have to go in here and include, actually let me include it in bootloader.h. I have to include the frames.h file to get, so that this guy knows what that is. Or should I include it here? I just want those squigglies to go away. Save all. Okay. Yeah, VS Code is interesting sometimes. Okay. Let me go ahead and compile this, or build this rather. Let me refresh, just because I've been making changes outside of Cube here. Refresh. Make sure everything can build. 0 errors, 1 warning. It's probably just because I've made a function and never used it. Let's see what the warning is. Defined but not used. Sure. Okay. And you'll always get, at least on here in VS Code, you'll get errors about your registers, but don't worry about that. Okay, so the send frame function will accept a frame structure, a pointer to the frame structure, and it will take that pointer, typecast it into a single byte, so that we can into a single byte pointer, so that it can serialize it across the Uart send function. So then the Uart send function takes that data and the length and serializes it. So that's it. Pointer frames and all this good stuff. All right, guys. So that should be easy enough to understand. Again, this is nothing out of this world. The next thing that I'm going to do is, not sure if I'm ready to do the Uart callback, because there's some other things that need to be in place for that to work in the first place. So some of those things that need to be in place for our Uart function to be able to do something is we need to define a placeholder frame, so that when we receive bytes on Uart, that we can have somewhere to assemble the incoming bytes into a frame. So I'll go ahead and I will post the callback, and I will kind of show you guys what it is that we need to have in place, right? Because it's easier to explain if you can see it here. Okay, so here's going to be our bootloader callback. So first of all, we're going to have to call this from the interrupt, which is in the main.c interrupt file right there. But we'll get to that in a second. Okay, so here's what we're going to have. We need to have a variable that's going to store the that really should be right here. That's going to store how many bytes we've received. How many bytes can we receive? I think it shouldn't be more than 255 anyways. I don't think so. Okay. Anyways, so and then we're going to receive bytes, and we're going to keep track of how many we receive. Basically, we're going to receive bytes until we have enough bytes to assemble a frame. So if bytes received count is less than the size of an entire frame, then keep adding these bytes to this bytes buffer. What is this bytes buffer? That's nothing more than just an array of unsigned integer 8. So, and it's, well, let's see. I'm going to make it actually, I don't know if I should make it global or just stick it in here. Let's just make it global, and I'll put it at the top of this file. I'm going to copy and paste from the other one. We're going to go up here, and we'll stick it right over here. Okay, so this is the buffer that's going to hold the incoming bytes, and it's going to be of the size of our frame. So now I hope this is starting to make sense. So we're going to receive bytes. As long as we have less bytes than it takes to complete a frame, then we'll keep adding the new bytes received into this buffer. Once the bytes received is equal to the size of a full frame, then we can reset our bytes count, and we can set this other global variable that I'm going to have to true. This has a lot of cleaning up to do, guys. Since I do want this to be a sort of state machine, then I have these sort of state variables going on, which I have not defined. So let me put that over here. So I do want to make this cleaner. I don't want to have these sort of little variables all over the place. So I think a cleaner approach, obviously, is going to be that we implement some sort of struct with states. So for the time being, let's put this here, even though states. So I have these bootloader state enumerations. So one of these states could be ready to parse or something along those lines. For now, the way I have my code written is I'm using this variable right now. And in my main loop, I'm checking that if parse is true, then I will parse a frame. But again, like I said, this is a work in progress. I'm, for the most part, trying to get the proof of concept down, which I already have. It's already working as a bootloader and it works just fine. And obviously right now I'm trying to get these video tutorials to catch up to the current state of the project where I'm copying all this from. Okay, so hopefully this makes sense, the bootloader callback. Now the next function that needs to happen is we need to be able to parse this bootloader frame. I'm going to go ahead and paste that function right over here. So parse frame looks like this. Let me include standard bool so this thing stops complaining. Received frame. Okay, so I need to make a frame called receive frames. This is going to be a global frame that's going to just act as a placeholder for whatever I receive on my down my Uart. So I'm gonna go back up here and just make a frame called received frame. Let me see if there's any missing things, because I want to do a test build where we are right now. Okay, let's go back to cube, try and build. Right click, refresh, where are you? And let's build this project. Bootloader.c, okay. Build. 0 errors, 2 warnings, send frame defined but not used. Okay. Okay, so everything works fine so far. Or builds fine. So here is the frame, the parsing function that's gonna assemble a frame. So if parse, remember at the end of here I've set it to true. So this parse frame will be called by somebody that's maybe checking this. So if parse, if we have a frame to parse, then the first thing we're going to do is we're going to consume that data. So there will no longer be, once we're done here, there will no longer be a frame to parse. So I'm going to go ahead and reset the variable. Then I'm going to do a mem copy of that buffer where I was storing the received bytes, this array here, of that into this received frame that I just made up here. So I'm going to mem copy those bytes into that frame, thus basically deserializing the frame. So my Uart send function is going to serialize the frame down, so it turns it from unsigned integers. It turns it from a frame into a whole bunch of unsigned integer bytes, and then this parse frame basically does the reverse. It takes a whole bunch of integer bytes, unsigned 8 integer bytes, and it assembles them into a received frame, and then this clears, and then this right here will clear that frame, so I no longer have not the frame, the buffer, so that it's back to zeros again. And then right here I do a very simple checking, right? All I'm checking is once I've assembled this frame, I'm checking if the received frame dot start of frame, which is our here's our, oop, that's not the one that I wanted, this one. So now at this point I've assembled a frame, and I'm just checking that the starter frame is equal to BL starter frame. So I'm checking that this is equal to this. And then I'm checking that the received frame dot end of frame, so I'm checking that this is equal to this. And that, so far right now, that's all I'm using to verify that I've actually received a frame. Obviously, to do is to check the CRC. That's really what you want to do, is to check the CRC of the entire frame to verify that you've received a valid frame. But I'm still up in the air about that, if I just want to check the payload, for example, or if I want to check the CRC of the entire frame. Anyway, so once this verifies very crudely right now that I do have a real frame, then I return true. Otherwise, I will return false. So whoever's calling this function will have something to do with that. Okay, so that is our Uart callback, our send frame, our Uart send data, and our parse frame functions. And I'm gonna actually make prototypes for all of these. Uart send, parse frame, what else? The callback. And the callback actually needs to be called from core source interrupt. Somewhere here there is a UART2 IRQ handler. This is where the callback will get called from. Make sure that builds, or if I have to include something somewhere. Okay, good. So everything's fine. Save all. Okay, everything's already saved. Okay, so that's going to be enough for this video, guys. And the next video, we'll go ahead and proceed and add more functionality to this. I will also, in the next video, give you guys, or you can go right now actually to my GitHub and find the repository that has a C# application right here that will send firmware to the bootloader application. Actually, no, don't even bother using this, because I just remembered this application is looking for a binary file on my computer. I'm going to actually go ahead and modify that by the time the next video is released, so that you can have like a dialog box where you can point this C# application to a file that you want to send to the bootloader. So by the next application, by the next video, hopefully we can have maybe some sort of working basic bootloader. Yeah, I think I'll do that just to get that out of the way, because maybe some of you guys are just itching to test it. And then we'll go ahead and implement the more the state machine, or we'll start implementing the state machine that will control the order of operations that the bootloader should have. Alright guys, thank you for watching, and do not forget to join the Discord or watch the or like and subscribe. I'm pressing the buttons on my thing and it's not showing my little subscribe stuff or whatever, so whatever. Anyways guys, I'll leave a link to the Discord down below if you guys want to talk about this or contribute. Somebody did mention that they wanted to contribute to the bootloader, but I did say just let my videos catch up to all the code that I've written for this already, so then that we're all at the same page. Alright guys, thanks for watching. Oh, wait. There it is. I got it to work. But it's not really working because I'm pressing the Discord button and it's doing that. Damn it.